Now let's go with the conservation of hypercharge. Now, according to this law, for any strong and electromagnetic interaction that can take place, the total hypercharge before and after the reaction or a decay process should remain constant. So I should say that this sigma y that we have, this sigma y must be constant for any strong and electromagnetic interaction. Now, let us go with an example. Let's suppose that we have a reaction of a proton and proton, and having lambda neutral, K neutral, proton, and a negative meson. Now, what is the hypercharge? I mean, what is this Y of left-hand side? This Y of left-hand side is simply 1 plus 1, that's equal to 2. And what is this Y of right-hand side is, okay, we have 0 here, no charge, and we have 1 here, okay, then we have 1 for P, and we have 0. So we have, so what can we say here is that since this hypercharge before and after the reaction is equal, so what is that? That reaction is possible through strong and electromagnetic interactions. Now, let us take another decay process. Say, for example, if I take a lambda neutral with a proton and pi negative. Now, the hypercharge of the left-hand side is simply 0. And the hypercharge of right-hand side here is 1 plus 0. And that will give us 1. So what's happening in this case is that the hypercharge before and after the decay is not same. When it is not same, that means the law of conservation of hypercharge is violated, and it's violated in this weak interaction. Now let's take another example of say if I have sigma plus P and a pi neutral. Now, let us see that whether this electromagnetic, whether this interaction is possible through strong interaction or electromagnetic interaction. Now, what is the hypercharge before the decay? The hypercharge before the decay is 0. So LHS is 0. And what is the hypercharge of the right-hand side? That is simply 1 plus 0, and that's equal to 1. So we can see that this hypercharge before and after the decay is not same. It's different. Therefore, the law of conservation of hypercharge is not conserved here. So I would like to say that the given decay is forbidden by strong and electromagnetic interaction. But at the same time, this hypercharge is not conserved in weak interactions. Hence, the given decay can take place by weak interactions. Now, from here, let's move on to conservation of strangeness. Conservation of strangeness. Now, according to the law of the strangeness, according to this law, this strangeness, which is symbolized as S, is conserved in strong and electromagnetic interaction. Strong and electromagnetic interactions. But strangeness is not conserved in weak interactions. So I'd say here that for strong and electromagnetic interactions, this delta S is 0. And for weak interactions, so this is for strong interactions and electromagnetic interactions. And this delta S is plus minus 1 for weak interactions. Now let's take a reaction. Suppose I have a proton and proton. I have lambda 0 plus k 0 plus p positive plus pi positive. Now let us go with the strangeness. So what is the strangeness of this is 0. What is the strangeness of this is 0. The strangeness of gamma neutral is minus 1. K, it's 1. It's plus 1. And P positive, it's 0. And pi positive, it is 0. So we can see here that the strangeness is conserved. The overall strangeness in the right-hand side is equal to the overall strangeness in the left-hand side. So I can say here that this del S is equal to 0. So the total strangeness is conserved. Now in this reaction, two strange particles, the lambda that we have and kaon, K0, with opposed strangeness are created along, they are created along with an outgoing proton and a positively charged pion. The law of conservation of strangeness, what it requires here is that at least two strange particles must be produced. If any strange particles are created in any strong or electromagnetic interaction, so I'll say that this phenomenon is known as associated production, what we have talked earlier about. That you have to have conservation and you have to have the products in some kind of pairs. Now the strange particle K0 and lambda 0, they are unstable. They are not stable. And they decay into light hadrons by weak interactions. And their lifetimes are very small, of the order of 10 to the power of minus 10 seconds. Now, if I go with this kaon, it goes with pi positive plus pi negative. And if I calculate this strangeness here, it's plus 1. For pi positive, it's 0. For pi negative, it is 0. So delta S here is minus 1. So LHS is not equal to RHS. Thus, strangeness is not conserved in this kind of decay. It means that the decay of strange particles, K0, by strong interactions is forbidden, as the lifetime of this decay is of the order of 10 to the power of minus 10 seconds, which is the characteristic of weak interaction. Hence, the decay of this K0 takes place by weak interaction. And we can have a similar consideration that we can put for lambda naught, where we have a proton and a negative pion with a lifetime of the order of 10 to the power of minus 10 seconds. Again here, what we will have is minus 1. Here we have 0 strangeness, 0 strangeness. So delta S is going to be plus 1. Now, if I consider the decay of the neutron by the weak interaction, what am I going to observe? Now, neutron into proton, an electron, and an antineutrino. Now, what is the strangeness of neutron? It's 0 for proton, it's 0 for electron, it is 0 for neutrino, it is 0. So what is delta S here? Delta S is 0. So we can say here that for weak interactions, delta S should be plus minus 1 or 0 in this case. And this is known as the selection rule. This is what's called as selection rule of weak interactions. So what we have delta S is plus minus 1 or 0. Now let's take another example to get more insight. Let us assume that we have K negative and a proton, and what it gives is K positive and chi X. Now, what we know here in this kind of reaction, we have various conservation laws are valid. And what is important here is that we have to apply those laws to find this chi, this X. So let's do this example, go with it. Now, for the very first thing is charge. Let's go with charge first. All right, so for charge, what we will have minus 1, then plus 1 is equal to 1 plus qx. Okay, so this implies this qx will come out to be minus 1. This 1 and minus 1 will cancel. This 1 will go on the other side of the equation. So qx is minus 1. Now second, let's go with the baryon number. Baryon number. Okay, so what we'll have for left, it is 0 plus, for proton it's 1, it is 0 for K plus some baryon number, Bx. So what is this Bx going to be? The Bx is going to be plus 1. Okay, Bx is simply equal to plus 1. Now, the third thing is strangeness. Now, for strangeness, what we have minus 1 for K minus, plus 0 for the proton, and 1 for K plus, and Sx. So from here, Sx will come out to be minus 2. The third component of isospin, third component, what is chosen as I3. What will be that? That will be minus 1 by 2 plus 1 by 2, okay? And here it will be 1 by 2 and plus, let me put it as I3. So I3 is coming out to be, the 2 will cancel, it will be minus 1 by 2. So the particle X is negatively charged, baryon, it's a baryon, with a strangeness number equal to minus 2. And so the particle X has the charge of minus 1 with its strangeness equal to minus 2. And its third component equal to minus 1 by 2. And these are the properties of hyperon. These are the properties of chi minus. So the particle that we have here is chi minus. So using the conservation laws, we could predict X in this reaction. Now let's go with another example. Say for example, I have pi minus a proton and kaon and some X. Okay, now what's the very first thing is charge. So for charge, what I will have minus 1 plus 1 is equal to 0 plus qx. So qx is going to be 0. This particle must have no charge. Point number 2, the baryon number. So for baryon number, what I will have 0 plus 1 equal to 0 plus bx. So its baryon number is simply equal to 1. Then the third thing is the strangeness. So strangeness is 0 plus 0 is equal to, for k0, it is 1 plus sx. And this sx comes out to be minus 1. And the third component of isospin, I3, that's going to be minus 1 plus 1 by 2 is equal to minus 1 by 2 plus I3. So I3 will simply, this will go on the right side, it will become 1 by 2 plus 1 by 2, that's 1. And 1 will cancel, so they will all cancel and you'll get 0. So what could be predicted about X? X is a neutral particle and it's a baryon with its strangeness equal to minus 1 and its third component of isospin is equal to 0. These are the properties of sigma 0 and lambda 0 hyperons. So this particle could be either sigma 0 or this could be lambda 0. Now let's take another example. And let us check whether this reaction is possible or not. I have a proton, and I get kaon and hyperon. Okay. Now, for charge, the very first thing, for charge I will have 1 plus 1 equal to 1 plus 1. So charge is simply conserved here. Now, the baryon number, that is plus 1 is equal to 0 plus 1. So baryon number not conserved. We can see here that the baryon number is not conserved because for K plus it's equal to 0. Now the third thing is the strangeness, and for strangeness for proton it is 0, for proton it is 0, for K plus it is 1, for sigma plus it is minus 1. So we have 0. So the strangeness is conserved. Now the third component of isospin I3. So for proton it is 1 by 2. Then again it is 1 by 2. And in the right hand side it is 1 by 2 for K plus and it is 1 for hyperon. So we can see here that this third component of isospin is not conserved. It is not conserved. Now, as we can see that the laws are not conserved, so this reaction is forbidden, strong reaction. It's a forbidden, strong reaction. And let's go with another example. Let's take an example of the negative pion and a proton giving a hyperon and 0. Now, looking for charge, the very first thing. So what is the charge? It's minus 1, then it's plus 1. From here it is 0 plus 0. So here we have 0, here we have 0. So we have conserved charge. Charge is conserved. The next point is baryon number. Now for baryon number, pi negative it is 0. For proton it is 1. For hyperon 0, it's plus 1 plus 0. So this is again conserved. Now strangeness, S. Now strangeness for pi negative it is 0, for proton it is 0, and for sigma 0 it's minus 1, it is plus 1. So we can see here that the strangeness is this is 0 plus 0, so it is conserved. Now the fourth thing is the I3, third component of isospin. So for pi it is 1, for p it is 1 by 2, and it is 0 plus 0, and it is not conserved. So this reaction is forbidden as a law of conservation of of strangeness is not conserved here. And when they are not conserved, so this reaction is also a forbidden reaction. So this way, we can treat any example, and we can check any reaction, whether this reaction is admissible, is allowed, or this reaction is not allowed, by making use of all of these conservation laws for the confirmation of those interactions, those decays that are taking place.